Neural networks are a cornerstone of artificial intelligence, emulating the human brain's architecture to solve complex problems. They learn and adapt from data, much like humans learn from experience. This adaptability makes neural networks pivotal in modern AI, powering innovations from autonomous vehicles to disease diagnosis. Their versatility reshapes industries and enhances technological capabilities globally. Neural networks mimic the brain's structure and function, offering a glimpse into AI's potential. They are integral to advancing human knowledge and capabilities, pushing the boundaries of machine achievements. Neural networks are inspired by the human brain's structure. The brain's neurons, interconnected through synapses, transmit signals triggered by biochemical reactions. Similarly, artificial neural networks (ANNs) consist of nodes or artificial neurons connected by weights akin to synapses. This design enables ANNs to emulate brain-like decision-making processes. Neurons in an ANN activate based on input, processed through a function that determines the output. This process allows neural networks to perform complex pattern recognition and decision-making tasks. Neural networks adjust their weights based on input data, much like our brains strengthen connections when learning. This learning ability makes neural networks powerful tools for AI applications. Every neural network's architecture includes three primary layers: the input layer, hidden layers, and the output layer. The input layer receives data, hidden layers process it, and the output layer delivers the final result. Hidden layers can have multiple layers, each learning different data aspects. This structure allows neural networks to learn progressively complex patterns. Weights and biases, adjustable parameters, are tuned during training to minimize prediction errors. This structure supports neural networks' learning capabilities and adaptability to various data and tasks. Neurons are the fundamental units of a neural network. Each neuron processes input and passes its output to other neurons. This process enables neural networks to handle and interpret complex data inputs. Neurons combine multiple inputs into a single value through summation, then pass it through an activation function. The activation function's output determines whether the neuron will fire and pass its output to the next layer. Neuron's design impacts the network's learning and performance. Understanding neuron function and organization helps design effective networks for complex tasks. Weights and biases are pivotal in how neural networks learn and make decisions. Weights control the strength and sign of input signals between neurons. Biases shift the activation function curve, providing flexibility to better fit data. Adjusting weights and biases during training allows the network to learn from errors and improve accuracy. This process, known as backpropagation, reduces errors over time. Fine-tuning weights and biases enables neural networks to adapt to various tasks. This adaptability is key to neural network success across different fields and industries. Activation functions are critical components of neural networks, determining whether a neuron should be activated. These functions process input sums and produce outputs for the next layer's neurons. Common activation functions include sigmoid and ReLU, each suited for different tasks. The choice of activation function affects a neural network's performance and convergence speed. Different functions can be used in different parts of the same network. Activation functions introduce nonlinearity, essential for learning complex patterns. They play a vital role in the network's ability to learn and make accurate predictions. Convolutional neural networks, CNNs, are specialized for processing structured array data like images. CNNs use convolution, a filter that processes input data sections sequentially, to produce a feature map. These networks learn spatial hierarchies of features, from edges to objects. CNNs excel at image and video recognition, classification, and medical image analysis. Convolutional, pooling, and fully connected layers process data efficiently. CNN's architecture makes them faster and less resource-intensive, ideal for image processing tasks. Recurrent neural networks, RNNs, handle sequential data like text or time series. RNNs incorporate loops, allowing information to persist, making them ideal for tasks requiring context. This mechanism provides memory, invaluable for language modeling, translation, and speech recognition. Training RNNs can be challenging due to vanishing and exploding gradients, but solutions like LSTM and GRU mitigate these issues. RNNs excel with sequential data, understanding and generating human-like text and predicting future events. Neural networks revolutionize tasks across various industries. In healthcare, they diagnose diseases with high accuracy. In finance, they predict stock market trends and automate trading. In automotive, they develop autonomous driving systems. In retail, they personalize recommendations by analyzing preferences. In agriculture, they monitor crop health and predict yields. Neural networks' ability to analyze vast data volumes makes processes more efficient and effective. Despite their potential, neural networks face challenges. They require large amounts of data to train effectively, which can introduce biases. Neural networks are often black boxes, making their decisions hard to interpret. They require substantial computational resources, raising environmental concerns. Addressing these challenges is crucial for responsible AI use. Efforts are underway to develop efficient training methods, improve model fairness and transparency, and reduce AI's environmental impact. The future of neural networks looks promising, with ongoing advancements addressing current limitations. Innovations in hardware and techniques like transfer learning enable faster, more efficient training. Explainable AI makes neural networks more transparent and trustworthy. As more industries recognize AI's value, neural networks integration is expected to grow. Neural networks have immense potential to solve pressing global challenges. The field is continually evolving, promising to redefine machine capabilities and enhance human potential.